Hello and welcome back to our coverage of Svp2016 from Salt Lake City. In the first episode, we spent a good chunk of time with Brian Switek and then getting to know the Permier Kickstarter campaign. In this second part of the episode, we hear from the conference's Roma Prize presenters. Dr. Alfred Roma was founder and first president of the Society of Vertebrate Paleontology. The Roma Prize recognizes an outstanding scientific contribution by a pre-doctoral student. Selection is based on the scientific value and quality of a submitted abstract summarizing an original research project. The prize is awarded based on the scientific value and quality of the oral presentation of that research during the Roma Prize session at the SVP annual meeting. We hope you've been enjoying this conference coverage, and we'll see you all again soon for the Paleontological Association's AGM in Lyon in mid-December. We'll see you then.
Hi, my name is Aki Watanabe, and I'm right now a postdoctoral research associate at the University College London. I got my PhD at the American Museum of Natural History in New York.
Okay, and what did you talk about for your Roma talk?
So I talked about my dissertation research, or a component of it, which is on the evolution of the bird brain from their dinosaur ancestors. So it's a unique system because I think most people know that birds are very intelligent. We have documented cases of them using tools. They have song learning. So it's a good system to learn about how this complex, highly enlarged brains evolved. And of course, this provides a nice comparative system to how our own large brains evolved.
Cool, and I know a lot of it's unpublished, so we're not going to talk about anything too specific, but can you just give me a general idea of what you did to look at these brains?
Sure. In general, my collaborators and I are interested in how the evolution of the brain, how that was driven by certain factors. For example, it could be environmental. Well, of course, we're looking at the transition from non-avian dinosaurs to birds. So the big change here is locomotion,
right.
Powered flight. So did the large brains and the brain morphology that we see in the fossil record, as well as modern birds, do we see signs of big changes in the brain shape when we look at the transition? Does it correlate with the acquisition of flight? And recent studies have shown that it doesn't, which is kind of unexpected. So now we're doing many projects, other projects, trying to figure out what is the precise or specific major driver of brain evolution along that key transition.
Yeah, so why would you expect it to change with that sort of a transition?
Right, so parts of the brain that are important for flight include the part of the forebrain that processes visual information, as well as the optic lobes. And we see expansion of both the forebrain and the optic lobes in the modern bird brain relative to reptilian groups,
okay.
Right? Sort of what you expect from, quote, primitive brains. And also you have the cerebellum, sort of the hindbrain, looking at, which is associated with the cerebellum, which is associated with motor control. So you actually see expansion of these key areas. So we would expect them to be more inflated and expanded in birds, and perhaps along non-avian dinosaurs that might have started to acquire flight or some type of flight like gliding.
Right. So have you looked at fossil and modern animals and compared things in that way?
Right. I think what's compelling about our research program is that we do have access to key dinosaurs, bird-line dinosaurs, that are very closely related to birds. And obviously, to study brains, the actual brain tissue does not get fossilized.
Right.
So paleontologists kind of work around that by looking at the shape and the size of the brain case, the empty space that used to hold the brain. And we know from other studies, previous studies, that in birds and mammals, the brain nearly fills up the entire cavity, that space. So it's a good proxy to use to study brain evolution through deep time. So paleontologists can actually peer into some of the neurological biology of these extinct organisms, which is very neat.
That's really exciting. So this is part of your dissertation from your PhD, is that right?
Mm-hmm.
Okay,
right.
And now you're doing a postdoc. So where do you see your research taking you from here?
Right, so I use some of the techniques I use. So I quantify the shape of these brain morphologies using sort of mathematical ways. So this is using not just sort of volumes, what are the proportional volumes of different regions of the brain. We're actually looking at how each part of the brain and also the brain overall could sort of changes. We can visualize which parts are changing, the localized changes. So I'm using that technique called geometric morphometrics to model these evolutionary changes that happened. So I use that on the brains during my dissertation. Right now, as a postdoc, I'm using it to model skull changes on actually squamates, which are lizards and snakes, and extinct relatives. And so I'm part of this big, actually, research that's going to look at skull evolution across what are called tetrapods, or four-limbed animals, which is a huge undertaking. So that includes amphibians, reptiles, mammals.
Wow.
So we'll see what we get. It'll be interesting to see what kind of similar but also contrasting mechanism actually drove skull evolution across all these animals.
That's so cool. All right, awesome. Well, we'll check back in with you once you have some more information on that. Thanks for talking to me.
My pleasure.
My name is Ashley Morehart. I'm a postdoctoral researcher at Washington University. I recently finished my PhD at Ohio University, and I study dinosaur brains.
Cool. And you gave a Romer talk. So what did you talk about in your Romer talk?
In my Romer talk, it was sort of a culmination of my dissertation work. So 6 years of work looking at how to get more information out of the brain cavities in the skulls of dinosaurs. So because dinosaurs don't generally fill their cavities, or didn't fill their cavities in life with brain, the cavities tend to not pick up a lot of information about the size and shape of the brain. But there are other pieces of information, other evidence of soft tissues on the brain cavity walls, which do fossilize, that give us information about things like blood vessels and cranial nerves and other features that can be used as landmarks to figure out and map out in three-dimensional space what the size and shape of the brain would have looked like. And then I use digital modeling to sort of put the brain back in that cavity based on those landmarks. And then I use the volumetric data I can get from those brain models to do statistics to test hypotheses about how the brain shape and size might have evolved in different groups of dinosaurs.
Okay, cool. So how do you get access to these areas where the brain was?
Wonderful. Yeah, right. Until sort of X-ray technology and CT scanning came along, folks that were doing work with brain cavities tended to fill the cavity with things like plaster or even latex to try and pull out a cast of that, using the cavity as a mold. They would take a cast of the cavity, and then that piece of plaster or latex would represent sort of the space of that cavity, and then the features on the sides of that cast would reflect whatever features were on the sides of those inner walls. Now so those used to be fairly destructive techniques, depending on how good you were.
Right.
And so fortunately for me, I have come along in paleontology after the advent of the use of CT scanning. And so similar to what you would have in a hospital setting, where you would do a CT scan on a patient who maybe had several broken bones, so more efficient than taking just plain film x-rays. You can do a scan through their entire body, and it's x-ray based, so it's just a series of of x-ray images that are sort of stacked together like a loaf of bread. And from that stack, you can get three-dimensional volume renderings of whatever you want, whatever anatomy is of interest to you. And we use a series of software programs to sort of isolate and extract digitally pieces of anatomy from those CT data. So then we have a 3D model of something like the brain cavity that we can manipulate and move around in computer space. So we can take the mouse and drag on it and turn it around and spin it, turn it upside down, whatever we need to look at. And that gives us the ability to see those features on the surface of the endocast without actually having to damage the fossil. Right. So it's non-destructive. And so once we have the digital endocast, and we can manipulate that in 3D space, we can also, or what I do is I tend to use other programs to do the modeling inside the cavity. So the first program that we use is an engineering program, an AutoCAD program, and that gives us the endocast. And then the second program I use is actually a modeling program, which is used by companies like Pixar and other CGI-based companies that do animation, and they build their 3D models to be characters, things like Shrek, things like the characters from Frozen. So Elsa is a CGI-based character. Oh, wow. I'm using the same program, but I'm using it to build dinosaur brains back into those endocasts.
That's so cool. That is really cool. So what animals have you studied specifically, and what can you tell us about their brains?
Sure. So one of the goals of my dissertation was to try and figure out a series of features that would show up pretty consistently on various endocasts across all of the different groups of dinosaurs. So you have sort of your classic meat-eating dinosaurs, bipedal, and then you have your plant-eating dinosaurs, whether they're the long-necked sauropods or whether they are more like duck-billed dinosaurs or maybe the armored dinosaurs like Ankylosaurus. And so I wanted to have a series of anatomical criteria to evaluate these endocasts that were broad enough that I could apply them across the board.
Okay.
And I did identification of criteria by looking at a couple of things, looking at the endocasts and what they could give me, and then I evaluated the brain cavities and brain shape and size in the modern relatives of dinosaurs, so things like alligators and crocodiles and gharials, as well as modern birds. And so using the information I had about their anatomy, I could infer anatomy from dinosaur endocasts. And so the dinosaurs that I looked at were, it was a very broad sample. And so I kind of think about my dissertation as being a mile wide and an inch deep. And so it was almost like a proof of concept thing where I could show that I could use these criteria across the board. And then the rest of my career potentially will be filling in the rest of that data set and just making it deeper and deeper. Because it's hard to compare brains across broad groups. It's hard to pin down why their brains might have different shapes and sizes because they are so very different in many ways. Their behavior is different, their body size is different. Yeah. And so looking at with a more narrow scope, looking at maybe just Triceratop and its immediate relatives, or just Brachiosaurus and its immediate relatives. If you compare brains in those smaller, more narrow samples, you actually can start to hopefully say things about why you're seeing changes in brain shape, because you might have some evidence about the fact that they were maybe more social than their immediate relatives or something like that, that gives you information about why their brain shape and size might be a little bit different.
Wow.
And so you can get more accurate in, more narrow and more interesting in your hypotheses, and more accurate in your results the more narrow you look.
So how would you be able to tell something like how social they were from looking at their brain?
So that's a tough one. There are lots of studies that show that social animals tend to, in some cases, have expanded cerebral hemispheres. So if you suspect that an animal had expanded cerebral hemispheres, you might hypothesize that they were potentially more social animals. So first you have to establish that, yes, indeed, they did have a little bit more expanded cerebral hemispheres. Right. Compared to their relatives, and you do that with statistics. Okay. And then once you establish that, then you make hypotheses about why that would be the case. So things like behavioral hypotheses, environmental hypotheses. And so unfortunately we can't observe extinct dinosaurs in the wild, right. So we do tend to try to work within the limits of our data. We don't want to be arm waving all day. That's not good science. Right. But if there are bone beds that suggest or footprint tracks that suggest that an animal is more social perhaps than its relatives, then we work work with the evidence that we have and try and look at the brain in a behavioral or environmental context.
It's amazing. It's so amazing that you can study the brains of extinct creatures, and their brains are so long gone.
Well, so to clarify, brains don't fossilize.
Right.
So we're studying the cavity, and so when I was developing and sort of beginning my dissertation proposal, I was talking to my mom about these ideas, and she said, "So you don't get access to the brains themselves?" And I said, "No, dinosaur brains, until I guess recently, this most recent discovery of the brain material potentially from Hastings is very exciting."
Yes.
But through the course of my dissertation, I had no access to dinosaur brains per se, just endocasts. And so my mom joked and said, and she's very sweet, she's a 10 out of 10 mom, but she did joke with me and said that I was going to be studying air for my dissertation, because the endocast is the negative, it's a cast of the negative space of that cavity, which is generally either filled with sediment or air.
Right.
And I said, "Yes, Mom, I'm studying air." Thanks for that.
It's related to brains, so it's super cool. So what are you going to be doing next? Where is your research taking you in the future?
So I am in sort of a transition period right now. So I finished my dissertation and defended that this summer. And then almost immediately, in like 1 week's time, I packed up, and my husband and I moved to Washington University in St. Louis. And so I'm postdocing there for roughly 3 years, and we'll see where this takes me. So I went from a department that was pretty heavily, dino paleo, although they do other things too, for sure. But my immediate cohort was pretty dino-centric, and now I'm in a paleoanthropology department, and so I'm learning all sorts of new and interesting things, and I'm fortunate enough that my methods are very similar to the ones that they use, so we can communicate, but we're just constantly learning things from one another, so that's a lot of fun.
Awesome. Thank you so much for chatting with me.
You're very welcome. It was a pleasure. Thank you.
I'm Daniel Field. I'm currently a postdoctoral associate at Yale University, and in early January I'm going to be starting as a prize fellow at the University of Bath in the United Kingdom.
That's so cool. Okay, so you just did a Romer talk. Can you tell me a bit about what you were talking about?
Sure. So I was talking about the origin of modern bird biodiversity and the origin of some of those features that today make birds unique, and specifically I was focusing on the origin of modern powered flying ability.
Oh, okay. So what sort of methods do you use to look at that?
I tried to address the various aspects of my presentation using a variety of techniques, phylogenetic analysis, allometry, kind of traditional morphological approaches.
Okay, can you explain what allometry is in maybe 1 or 2 sentences?
Sure. Basically, the study of how the relationship between anatomical structures change as organisms get bigger.
Okay.
And specifically, some of the work that I presented came about because I was interested in trying to develop improved methods for estimating body mass in the fossil record, because body size is a really important biological parameter that lots of other important biological parameters co-vary with pretty precisely, and therefore improving methods for figuring out how much an ancient organism would have weighed can actually help you understand a lot of different aspects of its biology, including to an extent whether or not a given feathered dinosaur would have been capable of flying. So I was interested in looking at a bunch of different ways to estimate body size, and in doing so I discovered that there's some correspondence between dimensions of the shoulder in modern flying birds and their flying potential, which isn't that surprising. But what's nice about that is the correlates that we came up with are correlates that can be readily applied to various fossil organisms. And in doing so, you can quantify to a certain extent the potential for a given organism to have flown like a modern bird or not.
Very cool. So what fossil birds flew?
These are the sorts of correlates that you can apply very easily to fossils within the crown group, so basically ancient representatives of the modern bird radiation. But what we were more interested in doing was looking at sort of a hierarchically internested suite of Mesozoic stem group birds. So these are taxa outside of modern bird biodiversity, basically what you might think of as feathered dinosaurs. And in doing so, we were interested in tracking basically where on the phylogeny of these organisms what we would consider to be basically modern powered flying potential to have arisen. And we argue that perhaps modern flying potential is something that arose later than has conventionally been assumed.
Okay, and is there any correlation between feathers as well with the anatomy, like the shoulder?
Well, there's a correlation in the sense that feathers and asymmetrical feathers specifically arose considerably earlier in the evolutionary history of these organisms than what we consider to be this index of flying potential. However, what's interesting about flight feathers when you look at things a little more closely is something that we demonstrated in a paper that was published last year, which is that despite exhibiting feathers that superficially look very modern, early feathered dinosaurs, things like Archaeopteryx, actually at a more microscopic level do not exhibit anatomically modern asymmetrical flight feathers. So in this paper, the lead author of the paper was Teresa Feo, a good friend of mine and a former graduate student at Yale. She discovered that asymmetrical feathers as well are a feature that actually arose much later in dinosaur history than had previously been recognized. And there appears to be some sort of correlation between the acquisition of what we consider to be fully modern flight feathers and the acquisition of other very important flight-related features like a robust, fully ossified sternal keel, which in modern birds is the structure on the sternum that the very large and powerful flight muscles attached to.
Cool. Okay, so what would you say your overall findings are from your entire PhD? What did you do?
Oh my goodness. Well, I mean, I was very fortunate over the course of my PhD. I was given a lot of intellectual freedom by my PhD supervisor, who's Jacques Gauthier at Yale University, and that allowed me to explore lots of different aspects of science that I found exciting. And so I got into molecular phylogenetics of modern birds and divergence time analyses, trying to figure out when in Earth history important divergences between major groups of birds took place, and some of this more functional morphological work looking at the bird shoulder and the bird feeding apparatus. And the opportunity to kind of get my feet wet and investigate all of these other aspects of bird evolutionary biology that I found interesting was incredibly exciting and rewarding, and it's something that I'm going to be forever grateful for, because I think it's really set me on my present trajectory, which is one that is going to attempt to bring together many of these seemingly disparate techniques and aspects of evolutionary biology to better flesh out how and when and why modern bird biodiversity came to be.
Awesome. Well, thank you so much for talking to me today.
Thank you, Caitlin.
Hi, my name is Haley O'Brien, and I am an assistant professor of neuroscience at Oklahoma State University's Center for Health Sciences.
Okay, and you gave a Romer talk, but we are not going to be discussing what you talked about in your Romer talk today.
Not just yet.
Not just yet. That's going to come out soon. But we are going to talk about some of the things that you're interested in research-wise, and one of those things is artiodactyls.
Yes, artiodactyls are my favorite group of mammals for so many reasons, and one of those is that they're an amazing evolutionary model. So we have a lot of artiodactyls today. These are animals that have an even number of hoofed toes. So these are things like deer, cows, pigs, hippos, antelopes, camels, basically anything that has hoofs that's not a horse, a rhino, or a tapir. So we just have tons and tons of them that are alive today. So we can observe their behavior, we can measure their physiologies, we can do all sorts of things. They also have an amazing fossil record. So I like to say that if you throw a rock back into the Cenozoic, you are going to hit an artiodactyl fossil.
Okay.
So we just have this really wonderful opportunity to learn about the entire history of this group, but also in the context of what they're doing today.
Cool. All right. Awesome. And so there's also a link between artiodactyls and studying them and environment. And what can you tell me a bit about that?
Of course. So artiodactyls have been around for a long time because they have a series of pretty remarkable physiologies. And we know that one of these is this specialized digestive system. So they have this 4-chambered stomach, and it's highly efficient for processing this really nutrient-poor vegetation. And that has helped them to adapt to climate climate change and to vegetation change. They also have this really unique way of tricking their brain into thinking that they are cooler than they really are. And this is called selective brain cooling. And what it does is it tells the centers in the brain that say that you're hot, that you're tired, that you're thirsty, basically turns those off. And these animals can go days or weeks or sometimes even their whole lives without necessarily having to drink water. So they're a really great model for understanding climate change because we can look at how they're eating, we can look at how they're responding to changes in aridity, water budgets, and essentially look at how these animals have survived the type of climate change that we're going to face now, but in the past. And then we can project that into the future to try and maybe have a better idea of how these animals are going to respond to this warming, drying type of climate that we're going to see in the future.
Cool. And so this is a lot of what you focused on for your PhD, right? So
Yes.
Moving forward now, what sort of research do you see yourself doing in the future?
Well, so right now I am planning on actually looking into more of the behavioral link between being able to trick the brain into thinking that it's cooler and how that's impacting what the animal is doing throughout its day, how that's reflected in a finer detail of the anatomy so that we can try to better figure out how these animals are using this really remarkable capacity to save water to their advantage. And from there, these are actually surprisingly not the only mammals that can trick their brains into thinking that they're cooler. So a lot of these charismatic megafaunas that we have today, so cats, hyenas, arid-adapted foxes, we also know that these animals are doing the same thing.
Wow.
And they sort of arise kind of together at about the same time in the fossil record, and they have fairly similar evolutionary dynamics. So the next step is to learn more about this physiology in carnivores, measure it in their behavior, measure it in their anatomy, and then again go back and look for how this is impacting their survivorship in the fossil record.
Awesome. Okay, great. Well, thank you so much for talking to me.
Sure. Thank you so much for having me.
My name is Lexi Jamison Marsh, and I am the director and producer of the Bearded Lady Project. The Bearded Lady Project is a documentary film and portrait collaboration to challenge the stereotypical face of science.
Okay, and you have an exhibit here at SVP. Can you explain to me what that would look like if the listener was walking by it?
Well, we set it up in a U shape, and so the first thing that you would happen upon is a 24 by 30 inch portrait, which is black and white. And our first person is Jenna Kempfer, who is a paleontological student. And she is standing at her field site in Hannah Basin, Wyoming. She has a very dominant pose, and as you kind of look up, you realize that she is wearing a big bushy beard that she braided herself. And the goal is to recreate these historic portraits of scientists at their field sites. And we wanted to do that with women, but to only change one aspect, and that was to give them a fake beard.
Okay, so where did the beard come from? Where did this idea come from?
I'm friends with a paleontologist, and her name is Ellen Carano. And as an artist, I've always been very fascinated about that other world. I'd never met a paleontologist before, and every time Ellen would return from the field, where she would go to Ethiopia for months at a time, I always wanted to know what it was like, what she had found. This was such an alien experience for me that it was, everybody dreams of being a paleontologist as a kid,
right,
but very few actually go ahead and do it. And I met someone who was actually doing it and living it. And at one point we sat down and chatted, and she said, I know how you see me, but I don't see myself that way. I feel like I'm torn in two different directions. I'm either celebrated and all eyes are on me, and I have to be the poster girl for all women in paleontology because I'm the only one. While at the same time, I'm being ignored, spoken over, and disregarded in my faculty meetings. And she said, I feel like I can't just go and do my job because I have these two battles to fight, and that if I had a beard that I could put on, I could literally just do my job, which is the dream that I've always wanted to live. And so I jokingly said, well, why don't you do that? Of everything that you've achieved so far, that seems like the easiest part of it. And so we kind of laughed about it. And then that night, the juices kind of started, and I couldn't stop thinking about it. And I thought, well, what if we did a video of you wearing a beard? Would you wear a beard? And then it just kind of snowballed. And so, well, what if we did a documentary? What if we included some of your colleagues? What if we, included portraits so that people could actually sit and look at these images and actually question, what does it mean to be a paleontologist if you just put fake facial hair on and you assume that that's a competent person who can go into the field and who can camp by themselves and be scientifically inclined. But if you remove that beard, all of a sudden that ability is taken away. What does that mean? So the project's pretty well exploded from our original idea. We were hoping we could get maybe 5 scientists. We've gotten over 100 at this point.
That's amazing.
It's been really a dream come true for me to do this creative project, but then to also, go into the field and experience all the different all the different research that these people conduct.
That's amazing.
Yeah.
So you've got 100 people. So you started with portraits. So you've taken portraits of all 100 of these scientists, or you're in the process of doing so?
Yeah, so we just wrapped at the Society of Vertebrate Paleontology. This was our final shoot. I'm flying to Denver today to begin editing.
Okay. So
the portraits have been going on. We've been filming and photographing women for the past 2 years. Mm-hmm. And the portraits at SVP are solos. So this is just a preview. There's still 60% more exhibition to be completed for the final.
Okay.
We wanted to initially seek out women in leadership positions because the main problem is that while schools and universities will brag about the 50-50 class ratio, if you look at the faculty, it's very different. And so a number of the women during their interviews said that they didn't notice a difference until they started applying for the same jobs as their male colleagues. And that's really when the challenges started for them. So we wanted to showcase women that had reached that level of their career where, they were on solid ground, they had really fought their way. But then when we went to UC Berkeley and UCMP, we also had a number of graduate students that wanted to participate. And I think that that's also really important, right, to hear all the stories, that there's a variety of women that participate in this. And so we did a series of lab representation. So we took lab portraits so that you could see how many women in each lab were present. So you would see maybe 4 in one lab, 1 in another lab, and did group portraits.
That's cool.
So those will be also a part of the exhibition.
That's awesome. And then I know that there was one portrait that was up of a woman who had a mustache that she'd actually worn herself in the field. Can you tell me a little bit about that?
That was Dr. Carol Hickman at the UCMP. And this was our second shoot at UC Berkeley. We had over 35 women who wanted to participate, and we did not say no to anyone. We wanted everyone to participate who was interested. And she wasn't interested at first, but a number of her colleagues had such a positive experience with this that they ended up convincing her, and she said, I'll do it under one condition. I want to bring my own mustache. And our team said, by all means, please, didn't really know the backstory, took her portrait, and then sat down for her interview. And that's when she revealed that the mustache was significant because when she was younger and working in the outback in Australia, she actually wore it so that people would leave her alone. That there's this sense that if you see a woman alone in the middle of nowhere, clearly she's incompetent and must be out of water, or her car must be broken down. Yeah. She couldn't be, a paleontologist that's actually conducting research and doesn't want to be bothered. So after, a few days of people coming up to her and asking if she needed anything and disrupting her work, she bought a big bushy mustache and slapped it on and was left alone.
That's amazing. So there's also a documentary that you're doing in association with this. So can you tell me about that, please?
The documentary film originally started out as a short documentary, but because of all of the interest, we've extended it to a feature-length documentary film. And this is a film that will follow a number of the paleontologists into the field, will showcase a lot of important aspects that I think don't exist in media these days, of women being competent campers, being physical, being scientifically minded, being passionate about their work, and really showing the journey that a lot of them have taken to reach their current career level. I think that you will see a successful woman and you won't know how she's gotten there. And I think for women, especially, the journey from point A to point B is often not a straight line. Yeah. There's time that's taken out, maybe because of mentors, you've changed directions in your career, or because of location. And I think for women that if you're not following that direct line, there's a sense of failure. And I really want to show that that's not the case, that a lot of times it's a more organic growth of a career than setting out to start something and then finishing exactly where you had hoped, which is often not the case.
Definitely. So what sort of feedback have you gotten from the project? Have you gotten any opposition at all?
Yeah, I think, this is a quirky project. It's weird. I think the most important thing that's come of it is that everyone who's participated has had a very positive experience. And that's something that I was very aware of and wanted to make sure that their trust was not lost. That being said, I think that this project allows people to give an opinion on a topic that's very difficult to talk about. I think that it allows conversations to start, whether you agree with it, whether you think it's almost too silly, to discuss a topic that's very serious, or, it doesn't really make sense to some people. But I think that the conversation is starting, and I think that that's the ultimate goal of it, that it doesn't have to, be a problem solver, but that it can lead to solving those problems and actually being aware. I think one of the most profound comments that I got from one of the men who came to the GSA exhibition, he said that the most heartbreaking part of this was not only recognizing the women who were in the portraits, but realizing that they felt the need to do this. And so that was very eye-opening for him, that he didn't realize that this was an issue for them. So it allows a little bit of empathy to get started, and some, hopefully, understanding and seeking out of how to better the situation.
Yeah, thank you for starting this conversation. It definitely needs to be something that's talked about. So what's the goal in terms of exhibiting the portraits and also releasing and screening the film?
The full exhibition will be revealed at the University of Wyoming in early 2017, okay. And then it will be a traveling exhibition. So academic institutions, art galleries are welcome to email us, info@thebeardedladyproject.com. And we're going to begin about, at this point in time, I don't see it stopping anytime soon. But I believe that the exhibition will stay at each location for about 3 months' time, and then we'll go on to the next location. The film will be finished also in early 2017. Distribution at this point is still up in the air, but I'm pretty sure that whoever hosts the exhibition will also get the documentary. And it is a nonprofit, so all proceeds are going to the Bearded Lady Project Ellen Carano Scholarship Fund, and that's being arranged by the Paleo Society.
That's amazing. That's great. And can you just tell me a little bit about the pledge just before we close up here?
So before GSA, we decided that we wanted to kind of take things a step further and ask people to make a pledge that, it's not just seeing and commenting on these portraits, it's really taking accountability for yourself. A lot of the women that have reached great positions in their career have done so because they've had great mentors. They've had people who haven't seen them as any different, who have pushed them. And I think that everyone has the power to do that, whether you're a woman, whether you're a man, to acknowledge that there are issues that can be easily remedied. I think most of these women are not asking for everything to change, but it's just an acknowledgement that there are differences, but to please, understand that everyone's here for the same reason, because they want to know more about the Earth. They want to know more about their research. So this was a pledge where we had people sign their names, list their institution, share their email address, and to just say, I respect differences and I will be there to fight for equality.
Paleocast was brought to you by Dave Marshall, with Joe Keating, Laura Soul, Liz Martin-Silverstone and Caitlin Colery. It was made possible by funding from the Paleontological Society and the Paleontological Association, but the show now relies on contributions from you, the listeners. If you've liked this episode, please consider donating, and thanks to everyone that's helped out so far. We'd also like to thank the Ocean Collective for use of their music. Please visit paleocast.com for the supplementary material to this episode and for our archive of past programmes. Subscribe to our Twitter feed @Paleocast and like us at facebook.com/Paleocast to get all the latest news.